Bill Magro is an Intel Fellow and Intel's Chief Technologist for HPC. He's going to be the moderator for the panel. He serves as strategist and provides software requirements into the product roadmaps. Joining him will be 5 panelists, John Lawson from Codeplay Software, Jeff Lowney from Intel, Eric Lindell from Stockholm University, Hal Finkel from Argonne, and Bharat Agarwal from Ansys. Welcome to the panel, and have a great conversation.
Thank you very much, Deb.
Thanks, Bill.
So welcome, everyone, and I hope you're enjoying your lunch. Today we thought we'd have a discussion about the world of heterogeneous programming, the world of heterogeneous architectures, some of the motivations, the challenges, and the outlook for efforts like oneAPI. So I think everyone knows that most codes are developed initially on CPUs, most algorithms, and then at some point it starts to perhaps make sense to target a specialized architecture. Perhaps it's because it's a code that has a tremendous computational intensity and a tremendous number of users, and so there's a payoff. Or it could be an area where there's been existing techniques, but they haven't been practical, like AI and deep neural networks. And with the right architecture for performance, the approach becomes practical and effective. But with the performance comes a cost, developer productivity, and this has been a key challenge, oftentimes leading to limited impact of these codes, or leading to even a fork in the code, which makes it difficult to maintain and keep up with the science or the engineering. So today we have an esteemed panel with us, and we're going to be talking through some of these considerations. So I'd like to say welcome to my panel. On the far end we have John Lawson from Codeplay. He's a staff developer at Codeplay, has been focusing on neural networks and bringing those to a variety of heterogeneous architectures. And he's also the initiator of a project called Sickle DNN, which optimizes for deep neural networks on heterogeneous architectures. We've got Bharat Agarwal from Ansys, commercial software development company I believe everyone's familiar with. And he focuses on the performance aspects of Fluent and in particular its scalability. So we'll bring a commercial perspective to our discussion today. Hal Finkel from Argonne National Lab is sitting in the center. Hal is the lead for compiler research and also parallel languages at Argonne. He's also Argonne's representative into the ISO C++ Standards Committee. Eric Lindell is a professor of biophysics at KTH in Stockholm, and he leads a team that focuses on protein dynamics and protein structure, and is known for very large-scale simulations with codes like GROMACS, and his team, in fact, leads the worldwide effort on GROMACS. And finally, we have Jeff Lowney, Senior Fellow from Intel, and Jeff is our Chief Technologist in our software organization, is also a primary architect of oneAPI. So welcome, panelists. So I'd like to start with a question for Eric. Eric, I talked about some of the trade-offs of heterogeneous architectures. It's a heavy lift, but you can also get a big benefit when you target a specialized architecture. I think you and your team have really kind of set the pace in terms of going after every shred of performance. So can you talk about some of the considerations that drove you and some of the challenges that you faced and the industry still faces?
Sure. I don't think it's necessarily unique to molecular dynamics, right? But both the curse and love of academia is that we're trying to solve the problems that haven't been possible to solve before. And if that means spending weeks, months, years of writing anything from assembly to CUDA to oneAPI, we will do it simply because it moves the boundaries of science. And that's both really difficult, but also exceptionally thankful, because you do things that computers haven't been able to do before.
So can you give a few examples? Can you give a few examples of some of the architectures you've targeted over the years and some of the challenges also leading up to heterogeneous architectures?
I think we've targeted pretty much everything, every single processor you've ever had in your car, everything on top 500, possibly not your toaster. Once upon a time, I think I wrote 500,000 lines of x86 assembly. But it's basically, if you give us a computer, we will optimize for it so that we can use it.
Well, I think that's great. And can you tell us a little bit about your experiences working with discrete accelerators like GPUs? I believe you support those in GROMACS today.
So we started working with GPUs, mostly with targeting AMD processors actually in the early 2000s. And then as so many others, we've mostly been focusing on CUDA the last 10 or 15 years, simply because that's where the market is. But we're of course interested in anything out there. And the challenge for us today is actually mostly that we have so many different architectures that we need to target. And as much as researchers want funding and everything, by far the hardest thing for us is to find talent. It's extremely difficult to find talented students who can not just port to these architectures, but also maintain and support them long term. So some of the things that we're most interested in oneAPI, if we actually can reduce these efforts so that we can write maybe not in one, but one target with some flavors. So that would save us gigantic amounts of time.
Jeff?
So can I ask, you say you want to hit, home run on performance on every device, but we're also talking about productivity and finding the experts who can support this. What's the trade-off there? And I mean, is 80% good enough if it's a shared solution, or do you really need 100% everywhere?
So that depends on what your target application is. So for GROMACS, I think we've seen some numbers, the latest USC said something like 5 or 6% of all the supercomputing cycles in the world are used for this program. So 1% performance is a lot of money. So no, we're not happy with 99%.
Yeah, and that's one of the reasons we love having you here. And for a little contrast, a different point of view, Bharat, why don't you speak about these same trade-offs and where you stand with adopting heterogeneity in commercial applications from Ansys, such as Fluent?
Yeah, just to add to that last point, we do see a variation in our customers' expectation of performance. Some people are interested in getting that one last % down. Some are not very interested. I could see them running 10% off, and they are fine with it. In terms of getting the heterogeneity, I think the market is exciting, and we want to be at par with it. There are certain pieces of codes we have which are doing different things like GPU. Well, it's different for us from traditional perspective, which is all CPU, right? So there it's very interesting because customers are very interested in asking for, and they are asking for these new hardwares to be utilized because hardware people are telling them they are so great and they can be used and leveraged and stuff. So we have to also leverage, and also there is a lot of area for us to do new things with that.
So I don't know the exact numbers, but a company like Ansys, which is a multi-billion-dollar publicly traded company and has tens of applications or more, likely has tens of millions or more of code, covering a very wide range of things. What is the tension between satisfying a customer who needs performance in a certain method and the challenge of bringing architectural changes to a code of that scale?
Elasticity is low in terms of migrating. Customers also want reliability. A lot of very advanced engineering firms, they have very long processes of validating a code release. Some of them have almost 3 months of validation of code, and then they adopt it into production. So from their perspective, they're also looking at the scientific accuracy, obviously. So all those perspectives go into building and asking. So for us to satisfy those needs, and that is not trivial for sure.
Okay, thank you. So I want to pivot over to yet another point of view, which is in the Department of Energy and Open Science. Hal, you work at Argonne at the Leadership Computing Facility. In the pursuit of exascale, both in the US and worldwide, what we're seeing is a proliferation of architectures. We're seeing heterogeneity taking root broadly, but we've got a world with multiple technologies for compute, multiple technology vendors, multiple system vendors. What are the challenges that you see from where you sit in your application community around this, and what kind of solutions do you need?
So there are really a number of challenges, and one is that from our perspective at a DOE laboratory serving an open science mission and with our sister laboratories serving other missions, we serve a wide variety of customers. So some of our application teams are essentially 2 grad students working in a university someplace. We have application teams that are internal and are well staffed. We have application teams that have large code bases and a very few number of programmers. So the challenges faced by these different kinds of teams are in many cases different. But I think that you can boil it down to being able to manage the trade-off between scientific productivity and the amount of effort it takes to program various devices. So having some aspect of performance portability is really important. It's also really important that there's a kind of tooling ecosystem around whatever the environment is, so that users can not only develop their applications, but they can tune them and they can debug them effectively. And also there's the education challenge is quite real. So, you know, we need to educate our users, and there have to be resources available for them in order to learn how to develop applications, small applications and large applications, and how to do so in a way that will allow them to run on a variety of different architectures.
So we've seen the Department of Energy develop frameworks such as Raja and Cocos as ways to recognize the value of heterogeneity, the value of specialized architecture, but also start to abstract some of the differences at the lower level, especially microarchitectural tuning level. There are a lot of analogs and there's kind of a mirror in what we're doing with oneAPI and Raja and Cocos. So can you speak to how you see the two relative to each other?
Yeah, so I think this is really quite important. So we have put a lot of effort into frameworks that allow us to abstract the kinds of things that we are concerned about in our applications to, you know, within a certain scope. So, you know, Raja and Cocos are really concerned with abstractions of data parallelism and of data layout and concerns like that. You know, we have other libraries that are developed within the DOE ecosystem in order to encapsulate things like linear solvers and adaptive mesh refinement and so on. So, you know, within these various domains, we develop these libraries and these abstractions in order to enable us to rapidly develop and deploy applications. You know, one thing that I think is really important when we think about oneAPI is that, you know, it also has the same kind of approach, right? So, you know, oneAPI has, a programming environment built around Sickle and DPC++, but it also has a number of companion libraries that are extremely important to a variety of different domains, from, you know, data analytics, machine learning, linear algebra, and so on. And, you know, what we're going to be looking at in the future is how we can take advantage of those within the application frameworks that we've developed.
Well, thanks for bringing up data parallel C++ and Sickle. So I'd actually like to ask Jeff a question here. You're an architect of oneAPI, and a prominent element of oneAPI, of course, is the data parallel C++. We get asked a lot of questions, which is around, with existing high-level languages, with existing ways to target heterogeneous environments such as OpenCL, you know, what are the motivations to introduce a new language like data parallel C++?
Well, we wanted to solve the problem that Hal was just discussing, which is you'd like to bring the abstraction capability of modern language like modern C++, but at the same time be able to express data parallelism in a way that goes all the way down to the metal so that we can keep the GROMACS team happy. So we wanted a language that had that balance. It had to be based on C++, so you could go high, but you needed to be able to drop down. And then the second is, you know, at Intel we really believe in standards. And you know, looking around, the Kronos group had come up with a C++, you know, sort of lift of OpenCL, which is called Sickle, and we thought that was a good starting point because it had been standardized, so a lot of eyes had looked at it, and it was a place that we could grow it to meet the needs that Hal mentioned.
Thanks. So John, you've been at Codeplay for a number of years, and you probably have as much hands-on experience with Sickle as almost any developer around. You've heard Jeff's comments about Sickle's a good starting point, which implicitly means there's some things where there's, you know, some things that could be improved or added. Tell us a little bit about your experiences working with Sickle across some different architectures and your view on data parallel C++ against Sickle as a baseline.
Yeah, so we've been working with Sickle at Codeplay since before it was called Sickle. I've been working on it for 2.5 years, building libraries and software through BLAS and DNN sort of kernels and compute acceleration through to Eigen and TensorFlow, high-level things. So Jeff is totally right that it provides a very good point from high-level stuff right down to low-level things. With the interoperability mode of if you have OpenCL kernels and things already, you can just sort of plug them in and everything just works. But also we had a fantastic talk this morning from James at Intel about all the extensions that Intel have been working on to extend Sickle and provide more features and better things that match some of the things that users have been looking for that aren't currently available in Sickle. And within Codeplay, we've been doing this as well. So most of the Khronos standardization process involves you internally develop an extension for the standard, and then you propose that standard, or that extension to the standard. So even though from the outside it may look like Intel are taking Sickle and changing it, that's actually how this standardization process works. And so hopefully we'll see some of these extensions being provided back into the Sickle standard.
Can you give an example of maybe one or two of those extensions where there's an active conversation now, and how what the reception is to those?
So there's a lot of discussion around the unified memory model going on at the minute. A lot of Sickle code currently relies on buffers, which doesn't match nicely with existing CUDA code or other frameworks that use pointers for everything. And so there is this tension of trying to, how do we provide Sickle supports in frameworks like TensorFlow that don't know anything apart from pointers. So what Intel have been suggesting has been this unified memory system of where the Sickle runtime will handle this memory pointer scheduling thing for you. Okay. And there's been a lot of discussion around this. I'm sure other people have some views on.
Yeah, I'd actually like to ask the other panelists if there's any particular areas, as you've looked at Sickle, you've looked at data parallel C++ that you see especially important or promising, or some remaining gaps.
I'll just say that from our perspective, obviously the unified memory support is extremely important. Support for reductions also is extremely important for us, and we've been Argonne is a member of Khronos, and we've been involved in the standardization process. We've been involved in this process, and as we have started using Sickle, we discovered some things that didn't work as well as we would have liked, and we've worked with Intel, and I'll compliment Intel on the extent to which they have been really helpful in working with us on things. So for example, the extension to Sickle that lets you omit the name of the kernel and the lambda name has been really important to our porting process to enable support for Cocos and Raja on top of Sickle. And so, these, based on the sort of feedback we get from experience, this is helpful. The other thing I just want to say is, based on my experience with standardization processes around programming languages in general, there is this trade-off where it's really helpful to standardize things for which you have implementation experience and deployment experience, because that's how you know you've gotten things right. On the other hand, the balancing factor is that you don't want to have too many divergent versions of things, because that fractures the overall community and makes portability hard. So, in all these processes, it's a trade-off. You have to balance these things somehow. So my impression is that the way things have gone about thus far is promising in this regard. So, there are these extensions, but they're being actively discussed with the community and also with the standards committee. And so I think that, to the extent that we can get implementation experience and deployment experience with these various features, and then also simultaneously pursue standardization is the best path that we have.
Thanks. So, speaking of Khronos, OpenCL obviously is one of its more prominent standards. And OpenCL got relatively broad support from technology vendors, but it didn't really gain a lot of broad support from developers. What's different about Sickle, and will we see a different outcome with it in data parallel C++? Maybe Eric, you'd like to comment.
I don't know. So OpenCL has lots of words. It's not it's not a very nice language to program at all. But what's even worse than the language, I realized that when we talked about Sickle, right? What's possibly more important is the entire glue, all the infrastructure code. How do we actually execute your kernels? And their OpenCL is completely horrible. It's like it's cruel and unusual punishment trying to start OpenCL kernels. I would love, of course, we love many things with Sickle. There are some problems. For beginners, I think it's going to be a challenge that the way you actually transfer data will in many cases be a bit different than CUDA. And CUDA has the advantage of being the first market mover here. I hope that this will catch on, but I think that will very much be a matter of execution. That making sure that this works so well, that it's bug-free and everything, so that it's going to be fun and easy to use it. And that, right now, everything we've seen now, it's amazing, enthusiastic, right? But the execution remains to be seen, and it's important to remember.
Yeah, so CUDA, of course, is well established and has had an opportunity to work through many of these things. Maybe back to John, you've got so much experience working truly not just in heterogeneous environments, but with many different targets. What has your experience has been with Sickle so far, and what do you think the outlook is for being able to create a common code base to target not just multiple architectures, but also multiple vendors?
Right, yeah. In Codeplay, we've been working with numerous vendors with numerous different types of hardware, from small mobile GPUs through to embedded platforms for self-driving cars, right up to large-scale GPUs as well. And Sickle provides a really good platform to target all these different things because of the way you can just write C++ and you can easily target hardware-specific features. Like some of the things that Intel have been working on in terms of subgroups maps very nicely to certain features within GPUs, but it wouldn't map to the embedded platforms. But there's no need for you to use, like you're not forced into doing these things. There are so many options within the framework that you can pick and choose for your specific target, which works really well.
So it sounds like you've had some pretty promising outcomes so far, and you're encouraged.
Yes, yeah,
That's
especially with some of the different chips that have specific hardware features for doing memory transfers and things. You can use features within Sickle to enable that.
So
really,
you're
really
getting the
effectively.
success of a general code base that's common, but then being able to specialize where you need to.
Yes, exactly. And the power of C++ with all the templates and the metaprogramming and that sort of thing can really give a lot of useful or helpful features to users in that sort of sense.
Very good. So, I mean, as we're seeing, it really comes down to the trade-off of the performance and the value you can get out of that versus the developer effort and developer productivity. And I think high-performance computing is an interesting, probably not unique, but a very interesting area in that it brings together advanced techniques in computer science and algorithms with advanced techniques in physical sciences and engineering. So, Bharat, I think Eric touched on this before, which is it's very difficult to find the right experts who can do both. I've lived that in a research environment. Can you tell us what it's like in a commercial environment, trying to find people who are able to do the physics, the engineering, and also do the computer science?
It is definitely, yes, very challenging, and we are always looking for very specific kinds of expertise mixed there. And it takes time to train and develop, and the perspective is also building in the existing code. So there is a lot of learning after somebody joins in the team. So there is that aspect as well. And then that's why learning something new is, we're always looking at the ROI for that. And we are already having our workhorses, and we are continuing to train new people on that. So yeah, it's challenging. The tools are there for new stuff, like CUDA definitely created a big framework for that and environment for that to provide support. So I think we are looking for that from oneAPI. Obviously, we are working on that, looks like. So, yep.
Okay, thank you. So, John talked about unified shared memory as one of the key innovations that is in data parallel C++ and is perhaps going to influence the direction of Sickle. This makes me think about the holy grail for developers of performance portability and the productivity that comes when you can start working with pointers in a common shared memory. I think we all know that it may not be a fully achievable target, but hopefully advances like Sickle and unified shared memory can actually get us closer. So Hal, would you like to comment on how you see this all playing out and how far we can get?
Yeah, I think that unified shared memory is it's a controversial topic in some sense in HPC, right? Because the way that this is traditionally implemented is with on-demand paging, and on-demand paging normally has performance overheads which are undesirable. And so, the way we look at it, though, is that when you have large existing code bases and you're trying to get them running on a GPU or some new kind of accelerator, what you really want to be able to do is have enablement technologies and then performance technologies. So you want to have technologies that enable you to get the application running on the GPU. And unified shared memory is a really important tool there because it means that the programmer doesn't have to go through and track down every little data structure that they may need to access at some point on the GPU and somehow get it transferred to the GPU and allocate memory for it and all of that. So when you have unified memory, you can elide that whole procedure and let the operating system and the runtime library and the hardware take care of that for you. Now, it's not going to take care of it for you in the most performant way in many cases. But for most of that code, it's not performance critical, so it doesn't matter. And then what you do is for the code that is performance critical, that's the code you want to be able to focus on and optimize. And for that code, you may do explicit memory prefetching or make memory copies, or and you may need to do this because you may want to reorganize the data or compact it somehow or whatever. And so the key thing is that some of these technologies are performance technologies, and some of them are enablement technologies. But the critical factor is that unless you have the enablement technologies, you may not get to use the performance technologies because you can't get the thing running in the first place with a reasonable amount of effort. And so that's why that's so important.
Thank you. Any other comments on unified shared memory?
No, we very much agree with that. Right? But focus on the 10% where performance really matters. So that when it comes to your kernels, you're not going to be happy with unified shared memory in general. But for all the other code, it's an awesome time saver.
Okay, thanks. So Eric, you've probably got, you're among the most experienced developers out there, you and your team, working with specialized architectures, working with a wide variety of architectural features in Intel products and other vendors' products. You've got a lot of experience working with CUDA, so you know its strengths and your weaknesses. Can you speak to why something like oneAPI and data parallel C++ would be of use to you and appeal to you?
So we're of course exceptionally interested in that we would have at least having the possibility of only writing things once and then being able to target multiple platforms. And when a new piece of hardware appears, in theory, it should just be a recompile and possibly some tuning away, rather than me having to ask the team that can we find a way to fit another 6-person month here so we can rewrite things from scratch to fit a new architecture. The other part really comes down to that most of the pain for us is surprisingly not in writing the kernels, because most performance sensitive kernels tend to be relatively small. They tend to be streamlined because we've optimized them for decades, right? And that's not hard. I can write any such kernel in a week, or probably an afternoon if my students do it. They're far better at it. But the glue code, it takes time. Just identifying what devices do I have in my system? Do we have the right drivers installed? What if I get an error code when I try to execute a kernel? And for us, that's 10 times more work. So I'm almost more interested in all the parts of standardizing how I access the resources. Once I'm down to a kernel, we can write any kernel.
No, that's a good point. And for those who have been in some of the oneAPI talks, we talked about the direct programming, we talked about the libraries, the frameworks. But there's also this low-level software interface that helps you enumerate and deal with a lot of the bookkeeping and a lot of the tasks that really aren't specific to the type of architecture. So you see that as an important area?
Hopefully a gigantic time saver for us, yes.
Great. Any other comments on that same question?
I'll just say that I think this is another key point of differentiation between OpenCL and DBC++. So, as was mentioned, the host side code for OpenCL is sometimes very verbose. And one of the key factors that we look for when we're looking at these heterogeneous programming environment models and libraries is, how do you reduce the effort to get the code running on the GPU? And the fact that you can do it easily in this case is very important.
That's great. So let's return to the question of standards. So we've got established standards like C++. We've got established standards like OpenCL, Sickle. Data parallel C++ is now on the scene. Intel is saying this is not something just for Intel architectures. We hope to see it influence standards. Maybe we could comment, John, on the prospects of data parallel C++ successfully influencing Sickle. How's it looking to you?
I think it's really good sort of as a starting point for adding new features to Sickle, because there are definite things in Sickle that are not great. It's a really good starting point as we are now, but there are lots of potential improvements that we need to make in the future. And DPC++, talking to some people from Intel, it's allowing them to move a lot faster than the Sickle standard is capable of. So we can see that the features coming into DPC++ and getting use and seeing how developers react to it, and then those features can feed back into the Sickle standard to help improve that as well.
Thanks. And so maybe if we elevate to what is arguably a larger question, which is the C++ standard. And Hal, you sit in a pretty unique space, right, in the sense that you're on the committee. From everything you see in terms of the bar that the C++ committee sets for new additions to the language, just the level of diligence and that needs to be done. What is the outlook of concepts like the ones you're seeing in Sickle and data parallel C++, and what's the timeline that we might see C++ embrace them?
So I think that the timeline here is actually quite reasonable. So we're just now in the process of finalizing what will be in C++ 20, in the 2020 version of the standard. And so after that, we'll work on the 2023 version and then the 2026 version. C++ recently added parallel algorithms, and one of the big downsides of that was that, sure, you could ask that an algorithm be run in parallel, but you couldn't say anything about where it would run. You couldn't specify information that you really needed in order to optimize for these kinds of systems. And so coming down the pipeline, we have a new concept called executors, which fits really nicely with DPC++ and the abstractions that are in Sickle. And there are other interfaces that are being worked on as well, dealing with affinity, dealing with the sort of two key things you need to do, which is say where you want stuff to execute, and say something about the data, so that you know whether how you can say how to execute things close to where the data is, or you could move the data to where you need the execution to take place. And those are the sort of key underlying concepts. And I think we are on track to having reasonable abstractions for those things in C++ 23. And I think there'll be a lot of commonality between the way that these are specified in C++ and how they are in Sickle. And this is in part because the communities have a lot of overlapping participants, and the C++ standardization process is learning from the experience with Sickle and DPC++ and Cocos and Raja and a bunch of other efforts in this space. And I think it will be even more mature in 2026.
All right, well, that's encouraging. Because, of course, the committee wants to see generality. And some of these, it's very easy to come up with vendor or system-specific solutions to these problems, but achieving generality is quite difficult. Jeff, did you want to comment on the standardization?
Well, I just wanted to say that Hal's describing this long process, but one of the ways to push it along is to implement things and get people using it, and then we get reaction and we learn. And what we've set up, in addition to this oneAPI concept, we have an open LLVM implementation, which is being developed by more than just Intel, though we're the dominant contributor now, so that we have a place where you can test out these new extensions and actually see how they work, how they compile, and how people can use them. So I think we're trying to provide a fast turnaround. It's going to be a product, but more of a laboratory than the long-term C++ evolution, which moves at a pretty slow pace.
Yeah, let me just add that when we're standardizing features, obviously one of the key things is experience, right? So you need to have experience developing something and also deploying it and have users use it and figure out what the pluses and minuses are before you standardize things. That's the best way of doing standardization. And so we were actually all talking about this backstage before we came out, that one of the key messages that we have to get across is, for everyone who's interested, these implementations are now available. Please go download them and try them out, because the only way that we're really going to be able to get the features right, either in particular implementations or especially in the standards, is to have user feedback, to have implementation and deployment and usage experience. And so that's really important. And the other thing I'd like to say is it's also really important that there are these open source implementations of the compilers, the libraries, and so on. because that really, really helps with this ability to deploy and experiment on large scale.
Okay, great. So one thing that I think we all know is that these problems are not new, right? These problems have been around for a long time. We have something in oneAPI, which is a new approach to tackle this problem. I think we all believe that the challenge is enormous. At the same time, the opportunity is enormous. So let's take it down one level more specific as we approach the end of our panel. And I'd just like to ask each of you to talk about what you think is perhaps the biggest challenge and what's the impact if we're able to overcome it with this effort. We'll start with John.
The biggest problem that we saw with OpenCL was like people didn't start using it. And so there was this complete lack of an ecosystem of software and stuff, feedback and things going on that in Sickle, we've tried to give the ecosystem a boost to get going, and the oneAPI libraries and integrations should help that as well. But as Hal was saying, without the user feedback and without this ecosystem, we're never going to get a critical mass of people actually using this technology. And so the big challenge will be actually getting
Just adoption, yeah. Okay, thank you. Bharat?
Yeah, from our perspective, I think the biggest in terms of gap, this only serves sort of a replacement for what we have for CUDA right now. But our main offering is relying on multi-node framework. So I think that would be a journey. We have to see how it unfolds, and that would be the challenge I see.
So really seeing how this composes with models like MPI for distributed problems. Okay, that's great. Hal?
Well, I'm going to sort of pick up on that a little bit and say that, one of the things that the challenges that we always have is predicting the future. So, figuring out, how do we architect a solution that will last us, into the future in good form. And, one thing I was thinking about last night was, DPC++ and Sickle are still set up around this sort of central coordinator model, right? Like there is a host CPU and it dispatches work to various places, and then you come back to the CPU and then you dispatch more things. And you could put things in queues and they can depend on each other and all of that. And that's true, but if I think about, okay, what is the future going to look like? How many different kinds of accelerators might we have? And how do we deal with, and in addition, if these things are in parts of distributed systems where there's also networking interfaces that have to be dealt with, are we going in the future to have to move to a model that's sort of less focused on having a central coordinating agent as a CPU? Because even the most powerful CPU in the world may not be able to keep up with a whole sea of accelerators and feeding work to all of them. And so I think it's going to be really interesting to look towards the future and see what kind of model will we want to have, and how will that change going forward.
Right, so we've got a model today where we're generalizing compute to run anywhere. We need to extend it to control and communications as well. Yeah. So, Eric.
So I would be a little bit more down to earth there. I think this sounds great for the future, right? But there is a challenge. It's not sufficient to be as good as CUDA because people are already using CUDA. So to get them to adopt this, it has to be better, easier, and for whatever reason, more portable than CUDA. And I hope that's going to happen, but it's, of course, CUDA has the advantage of having gone through roughly 10 generations or so of trial and error, and they've done tons of mistakes and gradually had time to fix them. So I think it's important not to aim too high initially, because it's easy to aim to design a perfect system, but what might just happen is that we never get it perfect, and in the meantime, people will stick to the system that work in practice.
Okay, thanks. And finally, Jeff.
So the issue that I think is the most important is this tension between productivity or portable performance and peak performance for a given device. And I think personally that we need something that functionally ports, and the performance gets you most of the way there, and then you can do some tuning. But if you have a language where you basically have to, even though it's in the same language, have to throw the program away to go to a new accelerator, that would not be a win. I mean, the goal here is to be able to write once, and tune multiple times rather than write multiple times. So that's what I see as the key thing that we're trying to deliver.
Yeah, and I think that ties back to Hal's comments about how unified memory can get you going, but then let you focus your energy where it's going to make the biggest difference. So this concludes our panel. I'd like to thank all of our panelists. It was really interesting getting the diverse set of viewpoints. And please join me in thanking the panel.